Today's quiz had to do with finding the exponential function that gives the principal on a $3,000 investment at a 7% interest rate, and we're trying to find again the exponential function p of t. It corresponds to that situation. Well, it should be obvious from what we've done that the function is $3,000, that's your initial quantity, times your growth factor, which is 1 plus your growth rate being 0.07, and of course we raise that to the power t. 1 plus 0.07 is 1.07, so we have $3,000 times 1.07 to the t. Another question, after 10 years, what's the principal going to be? Well, we plug in 10, p of 10 is $3,000 times 1.07 to the 10th, and that equals whatever you get when you plug that into your calculator. And then the average rate at which principal changes from t equals 9.9 to t equals 10.1. And we get that average rate by getting our change in p and dividing it by our change in t. Change in p is p of 10.1 minus p of 9.9. That is principal after 10.1 years minus principal after 9.9 years. And plugging that in, plugging these numbers into the function in this form and subtracting, we get approximately $80. Our delta t, our time interval, is 0.2, and that'll be 0.2 years. So that our delta p over delta t is $80 over 0.2 years, which is approximately $400 per year. The final question is, what function corresponds to radioactive decay where you have 200 decays per second at the initial time, and that rate is decreasing by 4% every hour. So we're going to have this. Our starting rate is 200. That stands for 200 decays per second. And it really wouldn't hurt to write out 200 decays / second. I ran out of paper here, so I didn't write that. The growth rate, since we're losing 4% every hour, the growth rate will be negative 0.04. The growth factor, of course, is 1 plus negative 0.04, and that's going to, of course, be 0.96. And then we understand that t is the clock time in hours. Now there was a question of whether we needed to express this 200 decays per second in units of hours. It turns out that that isn't necessary because we're never multiplying this 200 decays per second by the number of hours. The number of hours just serves as the exponent here, or let's look down here. That's the power to which we raise 0.96. We raise 0.96 to the t, and we just get a number. 0.96 to the second is approximately 0.92 something. I can figure that out, but I'm not going to do that in my head right now. That's just going to be a number that we multiply by our 200 decays per second. It wouldn't be wrong to express this as 720,000 decays per hour, but it's not necessary. If we had 720,000 decays per hour and we multiplied that by 0.92 or whatever we get when we raise 0.96 to the t, the number of decays per hour is just going to decay by the same proportion as the 200 decays per minute or per second. So that doesn't matter. Again, whether we have 200 decays per second or 720,000 decays per hour makes no difference.